We are Team Dino-Mite. I'm Brian.
I'm Alan.
I'm Grace.
I'm Arjun.
So the team name Dino-Mite actually comes from our backstory. So Gru knows that his children have been abducted and he needs to save them, but he can't do it himself. So he takes some time and invents a time machine, goes back in time and adopts a plesiosaurus, fabricates it with some mechatronics components, some extra arms, brings them back to the future, and they're going to help save Gru's children and the world.
So in order to get to the bot that we have now, we went through a lot of different iterations. We used all of our design tools that we learned in class, like the house equality, the function tree, the specification sheet, and especially the morphological chart, to choose which functions would be best for our robot to complete all the tasks. We have 4 main subsystems. The first subsystem is the wheels. So we wanted to aggress from a very, very early part of our design process because we knew that we would get the most points from aggressing, and that would give us the best chance of winning in the competition. So in order to do this, we just had a wheel-driven motor in the back of our bot. And what this would do is allow us to drive straight. We have 2 wheels in the front and keep it balanced. Then next we have the shrink ray arms. The shrink ray arms are powered by a mouse trap and released by a solenoid. The solenoid is triggered by the switch box in the front, which determines which zone. So when the switch hits the correct zone, the shrink ray arm will have its solenoid released, and the mouse trap will fling it forward, and gravity will fling it back so it doesn't touch the dome. The other anti-shrink ray arm is powered by a rubber band because the smaller solenoid that we wanted to use for it could not withstand the friction of the mousetrap, thus it would not retract and would not be able to release it. The next system we have is the missile clearing arm system. For that we have a arm that swings around the bottom of the bot. As it drives in, it's positioned so that it's on the left side of the middle missile, and when the moon arm raises up, a pin releases from place, and a rubber band powers the swinging arm and slaps the middle missile and the left missile out of the zones. Now the right missile is taken out by a mouse trap, so as long as we position the bot in good position, the mouse trap will take out the right missile. And then finally, the moon arm is just powered by a motor. It'll go up and place the moon on top.
Yep, so everything is powered by a MyRio, and the program we tried to make as simple as possible. It's just a flash sequence with each frame roughly corresponding to each one of these subtasks. And we tried to have as many physical triggers as possible, such as the wheels in the front to stop the driving, the 2 switches to control the solenoid arms, but we couldn't actually make the moon arm independent completely because we have the pin that also pulls the swinging arm.
So the overall fabrication, we like to use the bandsaw and jigsaw a lot. We like this form of fabrication because it gave us very hands-on control over exactly what we were building, and it also let us build very quickly. So we could sort of cut it down to size, lay it over the game board, and see how it could be positioned, see how maybe we'd score points or lose points with that exact configuration. And then we could kind of take it straight back to the bandsaw or jigsaw, cut it up a couple more times, and try it again, as opposed to sort of trying to CAD as close to possible, sort of looking at a frame of reference, or using the ideal measurements, because ideal measurements don't always work perfectly whenever you're going to laser cut something or 3D print it.
But for the fine and detailed design aspects, we use laser cutters for the components such as the curved shape of the moon arm, switch box, and stopper for the shrink ray arm. And when we look at the completion rate, we had 2 preliminary competitions, which we ranked 1 in our lab, and 2 weeks ago we had a qualifying competition which we ranked 1st in our lab section and ranked 9 overall.
So our main takeaways from this, we're starting off with fail early, fail often. We kind of thought of this from one of the first weeks. We decided that we would rather sort of think of maybe 3 to 5 iterations and test those and sort of see how we could fail on those and build off of those, rather than maybe think of 30 to 40 different iterations before we could test any of them. We thought this gave us practical results sort of right away, and it gave us something that we could build off of very quickly. Designing for the future, because the system of how the trials were laid out, with each couple weeks there was sort of a new task being added, we had that end goal in mind of the final competition from week 1, just so that we could try to keep building off of our current iterations, so we didn't have to sort of redesign each week, but we could really refine what we had going from week 1. Communication is key. We are 4 busy college students, and it probably took about 100 hours each to put into this robot. So finding the time that we could get together to do that, and also being able to communicate exactly what components we wanted where and how we wanted them to work in unison was very difficult. But once we sort of found a good way to talk and communicate, we streamlined that process really well. And then lastly, we figured that it had to be consistent, especially in the final competition. If you're not consistently scoring high every round, then you can get out in one of the first couple rounds and really not do as well as your robot can perform. So just being able to test it as much as possible and make systems that work on a consistent basis and rely on luck as little as possible. So that's our presentation, and we're open to questions if you have any.